Well, we're here today to talk about the history of radar, the history of NSSL. There seems to be a growing interest in this. And I remember in the early 2000s when I was the director of NSSL, there was some question about the value of OAR research to the operational agencies. And there was a blue ribbon panel put together that Barry and Moore, when he was still at New Hampshire, chaired. And I'll never forget, one of the primary results of that report was the single best example of research that led to an operational improvement was NextRed. So I think the people around this table had a lot to do with that. And there was also a socioeconomic study done by Simmons and Sutter that showed that the impact of NextRed on improved warnings resulted in a 40+% reduction in deaths and personal injuries from the improved warnings that came out through the Weather Service. So I think that's really proof of what a valuable program this was. Now there's some people that can't be here today, namely Ed Kessler, Roger Lermite, Dale Sermons, and Ken Wilk, who were absolute pioneers in launching these things. So I hope as we go through our discussions that we can mention their contributions whenever possible. So to start this thing off, the very first thing we're going to do is simply go around the table and state your name only, and we'll do some other things too. I am Jeff Kimple.
I am Don Burgess.
I'm Dick Doviak.
I'm Dusan Zinic.
Joe Friday.
Doug Forsythe.
And now we're going to go around again, and this time I want to know when you came to Norman and what you think your major contribution is to the NextRed program in just one or two sentences. So I'm, again, Jeff Kimple, and when I was chair of the meteorology department and dean, my contribution to NextRed was I kept the link alive between the NextRed program in Norman and the congressional and Senate offices in Washington, D.C.
I started, or I came to Norman as a student in 1967, and I started as a student employee at NSSL in the spring of 1970. I was fortunate enough to be able to contribute to the development of NextRed, the research done with all these folks, and to contribute to the deployment of the NextRed network. For a while I worked for the National Weather Service at the OSF and now ROC to help with that process. I also was able to contribute to the training because it was a big job in training all the forecasters on how to use this new Doppler radar data from the NextRad network.
I'm Joe Friday. I didn't do a great deal of work here, but I certainly benefited from the work that was done. The fact is, I was deputy director of the National Weather Service when we were planning for the modernization. And then when we were ready to start executing the modernization of the National Weather Service, I ended up as director. One of the worst things that can happen to you is to have to execute your own plan because you don't have people to blame for it. But I tried to maneuver, along with Jeff, the very intricate nature of Congress and the budget process in the federal government and all of those various activities to try to make sure that we were able to have the necessary funding to support the modernization of the National Weather Service. The Weather Service, when we started that modernization, was really out of date. We had over 350 locations across the country. Most of them were understaffed and under-equipped. The equipment we had was terribly out of date. The radars still had vacuum tube technology. And it was necessary to replace not only the office structure, it was necessary to retrain the people, and it was very important, the work that you helped here as far as training people to operate on the radar. It was necessary to replace the equipment and to change the whole way we were doing. The people at Norman, both in the School of Meteorology and National Severe Storms Lab, and the various other activities that were here with the ROC and with the training center, or the training branch and all of that, were absolutely critical to making that modernization work.
You also were very helpful in bringing spare parts to build a radar here, which is...
That's another story.
Okay, later.
I came to Norman in 1978. I was part of the Air Force at the time. Air Force officer, and I came here to get my master's degree, but the primary reason I was here was to be part of the Joint Operational Doppler Project, or Joint Doppler Operational Project, JDOP. And my contribution to that was I wrote some of the first real-time algorithms for Doppler radar, and we automated a tracking system that we brought and from AFGL, and then I later went on to become the deputy to Ken Wilk here in the interim operational test facility, and we ran various testing operations. We went to a program up in Boston. I was all part of that testing. Later on, I became part of the National Severe Storms Lab as a special projects person here, and worked with the continued development of the NextRad radar, working with the Norman Doppler and Cimarron Doppler.
Well, I first came to Norman in 1973 as a postdoctoral fellow to work with Dick Dovliak on various aspects of NextRad and the Doppler program. And then I visited for a year in '75, and permanently I joined in 1978. My initial contributions were in the areas, for example, of developing and evaluating various signal processing techniques for the Doppler measurements, and then in measurements of distribution of velocities in violent tornadoes. So we had some of the first of these, and also development of tornado vortex automatic identifications with Larry Hennington, if you recall, and then Tom Burgess. But by far my biggest contribution in all of my career is this development of dual polarization on the NextRad, but that is subsequent to the deployment of the NextRad.
Yes, I came here in 1971 at the invitation of Edwin Kessler. You might ask, why did he invite me? Well, one of my colleagues at the University of Pennsylvania, a student of mine, a student colleague, became director of the EE department here at the University of Oklahoma. He mentioned my name to Edwin Kessler. And probably another reason is that I was starting a remote sensing research program at the University of Pennsylvania, and I think Edwin heard about that, invited me out. And at that time, it was a very difficult decision to make to come to Oklahoma. I had two job offers, actually, Oklahoma and Air Force Cambridge Research Laboratory. And my advisor, PhD advisor, was encouraging me to stay in the East Coast and in Massachusetts and stay with the Air Force Cambridge Research Laboratory. But the big attraction of coming to Oklahoma was the University of Oklahoma, working with students here, being able to teach courses. So that tilted the balance that I came to Oklahoma in 1971 to head up the Doppler Radar Research Project.
Do you want to mention your major professor's name?
Actually, my major professor's name was Dr. Lombardini.
But who was the
But
guy?
the Lombardini was on sabbatical, and Leon Zelby, Dr. Leon Zelby, who was the director of EE department at the time, was advising my final year of my dissertation.
Okay.
And actually, Leon Zelby brought your name to the attention of Edwin Kessler.
We had invited Roger Brown to be here, but he's ill today, so we're going to ask Don to fill in some of the things we planned on asking Roger, because you were here in the very, very early days. So if you could tell us how NSSL got involved in Doppler weather radar, and a little bit, if you could mention about Dale Sermons and Roger Lermite.
Well, Ed Kessler brought in Roger Lermite to head up the radar program with the intention of developing Doppler radar, Doppler weather radar. And Roger trained Dale Sermons, who was first a technician and then an engineer. Roger then left NSSL, Dale stayed, and NSSL got the opportunity to get a Doppler radar. And it was surplus from the military, defense application, These were radars that were configured for point targets, airplanes and missiles. The first radar we got actually was a two-line warning radar, surplus by the military when they got a newer version. And then under the leadership of Dale Sermons as chief engineer, that radar was reconfigured for distributed targets, the precipitation, the weather that we look at. Then we acquired a second radar. First radar was in Norman, and then we acquired a second radar we put out at what was then Cimarron Airfield. And maybe 25 miles west of Oklahoma City, so we could do dual Doppler studies.
Okay, thank you. So Dick, what was your first priority when you came to Norman?
Well, I was heading up the Doppler radar project, and there were two maybe high priorities. One was the dual Doppler network to make sure that was implemented to study the dynamics of severe thunderstorms, so the meteorologists would have a better understanding of the growth of thunderstorms.
The full three-dimensional airflow.
Three-dimensional flow of winds and side thunderstorms. The other priority was the building of a real-time display. And I think the NSSL had the very first real-time Doppler velocity display in 1972, as a matter of fact. It was built by Dale Sermons, and Dale, I have a paper here by Dale and myself. Dale's the lead author for that paper. And I think it was based upon very simple ideas, but it worked. Other institutions were building complicated spectral analyzers, which are very, very difficult. We followed the advice of a friend of mine, Dick Strauch, at the W Propagation Laboratory. Keep it simple, make it work, show something. And in less than a year, we were able to show this real-time display. There's a paper by Don Burgess and Les Lemon, Dale Sermons, lead author, and myself, showing a Doppler isotachs of a tornado. We detected the first tornado in real time with that display.
So speaking of that first tornado, what breakthroughs happened with the Union City tornado? So Don, could you tell us about that and the discovery?
Well, the Union City tornado was very important to our research. Now, Dick was really talking about a tornado that occurred earlier than that. It was the first one we observed. But the first very significant, violent tornado we observed in real time with multiple radars, because not only was the NSSL Doppler involved, but the Air Force Geophysics Lab had brought equipment down and was also collecting data on that storm. So we had really good radar data. We had storm intercept teams in the field to record the visual aspects and was there really a tornado and what did it do. And so we had a veritable gold mine, although we maybe didn't realize it at first because it took a while to process all this data. Computer power wasn't then what it is now, and we actually couldn't process it in Norman. We had to go to NASA in Houston to process the data, and it took months.
So
But in that data then, we discovered signatures that we use today. The mesocyclone signature was known, but we discovered a tornadic vortex signature that depicted for that big Union City tornado exactly where the tornado was located.
May I add, that was also the first time that the Doppler spectra were collected from the tornado and displayed the distribution of velocities and demonstrated exactly what is happening on a small scale inside this resolution volume. And so that was...
Yeah, that was an aspect. There were many aspects to the study. Roger Brown, who couldn't be here today, actually headed up the overall study of these different aspects. Another important aspect was the storm electricity and lightning. Bill Taylor had lightning equipment, and there had been a controversy in the 60s going into the early 70s about did lightning generate tornadoes? Lightning produces heat, and could repeated lightning strikes generate enough heat then to cause a swirling and tornado? And Bill Taylor's work and the radar data and the other things that we got on the Union City tornado was one of the cases that showed conclusively that, of course, lightning is important in thunderstorms, but lightning was not generating the tornado.
Okay. So we all know that NextRed is a try-and-see program. Right now it's housed at NSSL. So Doug, when you came, what was the Air Force's interest in being involved in this, or what were the circumstances?
Well, the Air Force had been working back in the early 60s on Doppler radar. They'd actually put together a 5-centimeter Doppler in 1961, and they were interested in replacing radars for the Air Force. The Air Force had the FPS 77 and the CPS 9, and those radars were old and being hard to maintain, so they wanted to replace those, so they were looking at technology at the same time of how do we do that, but then they were working on the Doppler effect and actually put together a plane shear indicator was built by them that actually showed the first mesocyclone. And they captured that data up in Boston, I think, is where they actually captured it. But Donaldson wrote a paper back then about the mesocyclone and the rotation going on in a thunderstorm. And so they had this interest, and that brought us up to JDOP, so the Joint Operational Project. And why all three came together, I'm not sure of that detail. But
one of the things that came out of the presence of the Air Force is their C-band radar, the 5-centimeter radar, in which Don Burgess showed with some studies that the shortcomings of the 5-centimeter radar with respect to attenuation, that they were missing some tornado vortex signatures.
that happened in '79 with the
79.
Wichita Falls.
Yeah, exactly.
Both the
Right.
5-centimeter and the 10-centimeter were both here. AFGL's 5-centimeter
Right.
didn't see the storm at all. They were attenuated, and the 10-centimeter saw it.
And of course, that data was important scientifically then for us to choose 10-centimeter wavelength S-band as the radar for the network, for NextRad. But then during the 1980s, as Joe Friday is only very much aware, there was this feeling in government and the private sector thinking, well, maybe this 5-centimeter can do the job after all. And those data then paid dividends to be able to conclusively show we were going to miss tornadoes if we went with the 5-centimeter instead of the more expensive 10-centimeter.
Well, it wasn't just missing the tornadoes that mattered too, it was also the attenuation of the signal itself. And that was most notably illustrated by the Southern Airways flight disaster that occurred around that time, in which an aircraft thought that there was nothing ahead because it was dealing with 5-centimeter radar. And because of the attenuation, it ran right into the middle of a major thunderstorm and was basically lost all lives on board. So it wasn't just the tornado itself, it was just the attenuation
But that
of
was
heavy precipitation.
I think that was an airborne radar.
It was an airborne, radar,
And he had this short wavelength, I think it was 3-centimeter.
3-centimeter radar.
And he thought he had a shot through a narrow corridor and missed a heavy-duty thunderstorm. He flew right into the middle of a heavy storm.
That's correct.
Also, precip estimation. Our ability to estimate rainfall is affected when we have that attenuation.
I might take a little bit of time just to illustrate some of the goings-on that brought the three agencies together. That story is worth telling, I think. I recall right after I went to the Pentagon as an Air Force officer, working on the Secretary of Defense's staff, so I was representing all of the agencies. I got a call that I was supposed to go over to the old executive office building next to the White House and meet with, that was where the Office of Management and Budget was located at that time, and meet with the person there that was managing the NOAA budget and was interested in all of the various environmental type of activities. So we had a representative from the FAA, we had a representative from DOD, which I happened to be, and then we had a representative from the Department of Commerce representing NOAA and National Weather Service. The OMB examiner there basically said to us, you know, we're trying to look at ways of improving the government. There's only two things that the government does that affects every man, woman, and child in this country. One is the Postal Service, and one is the Weather Service. And it's about time we started to get one of them right. So basically, at that point, the three agencies were directed by the Office of Management and Budget to work together on joint weather programs to benefit from economies of scale, from commonality of equipment, the whole thing here. to deal with so that we could outfit all of the weather agencies. The FAA's necessity for weather radar for aircraft operations, the DoD's necessity for weather radar for all of their military operations, and of course National Weather Services. So that was the beginning of the tri-agency program. And we had that not only on the radar program, we also had it on surface observing systems as well. So that brought those things together. That's one of the few things I think that OMB did that was wise. Now, I will admit, when I went back to DoD, and I told the Air Force that we were going to join with the National Weather Service to do that, I was told that I would never be welcome back in the Air Force again if I insisted on that. But we did it anyway, and I think it benefited everybody concerned.
Yeah.
And I think one of the things that was done, very important and really helped, and that was that FAA personnel and Air Force personnel came to Norman with Weather Service people to actually work in the Joint Doppler Operation
Absolutely.
Project. So it wasn't somebody else's project, it was their project, and those people who participated could carry the story back and tell others and convince the world that this was, Doppler radar was a good thing.
In fact, Joe and I were talking about one of those stories that we carried to the Air Force was the hailstorm that hit Vance Air Force Base, and we were able to make that prediction that we'd seen the mesocyclone. We made that prediction that there was going to be large hail. They'd actually put some of their aircraft. We saved, I forget how many millions of dollars.
52
well,
million was the number I was.
It's interesting you brought that up because Joe, the general from Vance, and myself testified in front of Congress, and when I left that testimony, I thought that the general at Vance did the best job. He really sold it on how important it was to have that advance notice from NSSL and to move the aircraft into the hangars and protect them from the hailstorm.
Doug briefed the results of that to a senior Air Force general and got more or less Air Force buy-off. I took the results of that one particular storm to the Undersecretary of Defense for Research and Engineering at the time, Bill Perry, who later became SecDef, and convinced him that DoD should support the Next-Gen type of program from the overall standpoint. So that one storm, the JDOT project in that one storm, was used to really grease the skids, if you would, in the military so that they were fully involved in the program.
That same cooperation might be carrying forward to the future radars, because there's a program called Multifunction Phased Array Radar, where the surveillance function for aircraft, weather, will be joined into one radar system, with the savings money for using this common radar for all three functions.
So Dushan, what's the big deal about pulse pair processing?
Well, at the time it was a very big deal. As Doviak already mentioned, NSSL invented a simpler version of the pulse pair processor, which really ignored the amplitudes of the signal, but computed the phases, and from these phases they were able in real time to obtain Doppler measurement. And that was 72, 73. It was very, very early. Well, in the community outside of weather community, including astrophysical community and some others, it was known that if one takes the amplitude and phase together of the signals and combines these in a very simple manner, one can get a very, very good estimate of Doppler's motion, of mean velocity, and the Doppler spread. And that was possible to do at the commensurate speeds with existing processors. Actually, processors had to be built specially for that, but they were not exuberant in price nor complexity. They were much, much simpler than these big racks that required full analysis and spectral processing. So one of those was built then by Dale Sermons and technicians at NSSL. I believe it was 74, 75, if you recall.
Something like that.
Something like that, 75. And so that was a very successful engineering development that was immediately used on the Cimarron and Norman Doppler radars and produced fantastic results for, well, I would say, for maybe 10 or 20 years. Later on, the displays were used to show this in color. And, but keep in mind that that was well ahead of these fast computing devices that came much, much later in the 90s.
It was really our ability to have real-time displays and to have pulse pair process, octave change counter, then pulse pair processing that allowed us to go and do JDOP.
Exactly, and to see in real time, you just mentioned a very important point, to see in real time what's happening in the storm on a scale of a few hundred meters. But I would be amiss if I didn't mention that the real-time display of spectra, of the distributions of velocities in the tornadoes, not just mean velocity, but the distribution, like between 50 and minus 50 miles per hour, you see at every location, spaced maybe a few hundred meters in a radius, was also made by Larry Hennington and Alan Zahavi. And that was also a unique capability that was not replicated maybe 20 years later.
Can we kind of follow up on that, because with the Union City tornado, people drove to Houston so that you could finally look at the data and identify the tornado vortex signature. Now we're talking about real time. I mean, that's like orders of magnitude different. So what happened to make real-time Doppler information available?
As I said, it was the possibility to build this device, this Pascal processor, so specifically designed to do these 2 or 3 computations, to compute power, to compute Doppler velocity and spectral width. So that was a device in a rack like this, about that.
But the displays weren't colors, so how?
Well, the displays were not colors.
Shades
So the
gray.
first displays were black and white.
Shades
Right,
gray.
so how did you do it?
Well, Dick can say, you remember the shades of gray?
Yeah, well, I have a picture here if you'd like to look at it. This is the black and white picture. The
Okay.
and
Shades of
the biggest
gray.
problem we
Also,
had
I remember
was to
the little
identify.
speedometers.
Yeah, that was,
The biggest problem we had was to identify the difference between outgoing velocities and incoming velocity, because that defines the vortex signature. But Dale Sermons came up with a clever way of strobing the display, so
Okay.
you can distinguish between outbound velocities and inbound
The
velocities.
strobes and the shades of gray.
Yes.
and
But there was also development going on at AFGL at the same time on color displays. They went to Raytheon and had the pulse pair processor built and produced color displays. It was called a scan converter, but you actually saw the various features in color. And that was brought to JDOP in, I know, 78. I'm not sure about 77 if they brought that instrument here or not.
No, it was there both years. We
Yeah.
also had our color display.
Yeah.
First time we had 2 sets
Yeah,
of color.
yeah.
Do you remember what year that was?
prior to that, I want to address,
77.
I want to address Jeff's remark that he remembers some arrows. Well, that was again a very clever invention by, I believe, Larry Hennington,
Yes, Larry.
who used arrows as little speedometers. And the size of the arrow pointed the direction of the wind, and the angle was, I mean, the size was the strength of the wind, and the angle was the direction. So by putting
In the
these
size of the airhead was the spectrum.
spectral width,
Yeah.
and then putting that, all these arrows on a screen, you could pinpoint the location of the rotation or the full line or the gastron. So
You
it
could
was
zoom up to look at just a few gates.
just exactly the location to within few hundred meters.
So do we need to say anything else about 3, 5, 10 centimeter and how Nexred ended up 10 centimeter? I mean, is it really that,
Well,
I think we covered that
Yeah.
a while ago.
I would say, when you said what allowed all this to occur, it was the tremendous growth in digital technology in the 1970s. When I started school in 1967 at OU in meteorology, which was in engineering, my first course was use of the slide rule. We did not have digital calculators, we didn't have digital devices. We went from that to 10 years later, we had computers that were fast for then, that could do real-time work.
But of course, the personnel had to use them very, very intelligently. And I remember Larry was telling me this. He said, when say, type a word like go, G-O. I type G in between, the computer does something, and then O, it comes back, and again, it was such a clever programming, such a detailed programming that there was nothing wasted. Every pause was used for computing. So, you know, it required a lot of ingenuity and hard and dedicated work by the people to make these run in real time commensurate with phenomena.
So Joe, you want to tell us any more about how things evolved or developed or happened in Washington that made this whole thing possible?
In Washington, as is still the case today, there's one major concern on all of the programs, actually two. One is effectiveness and the other is cost. You mentioned several studies that were done talking about the cost benefit for what we were trying to do in modernizing the National Weather Service. One of those cost benefit studies basically showed that for the projected gains that we had, and you mentioned the projected gains as far as the accuracy of forecasted warnings were concerned, but as far as the overall economic benefit, for every dollar that we were planning on spending for the modernization, there was an expected return of $8 to the general public as far as the improved economic benefits from improved weather forecasting, from better warnings, and so forth. Even with that large number, budget was always an issue. Even after we had the NextRad program approved, and I'll mention how that came about in just a moment, even after we had the NextRad program approved, there was constant pressure to reduce the prices. One of the first things that was done was to say, well, we only really need the Doppler system in the severe weather area. So we don't need it other than in the tornado alley and all of that. And we'll just put standard, non-Doppler radars elsewhere. We fought that and got rid of that. Then the idea was, well, we don't need the 10 centimeter radar every place. We can put 5 centimeter in other areas as well. And we finally got that stopped. And then, as a result of something that I won't even go into in this because, I won't go into it. All of a sudden, the program came to a halt with the direction from our political appointees above to study using off-the-shelf systems as opposed to the Doppler radars that we were trying to build. And the off-the-shelf system that was designed to be studied was a 5 centimeter WSR-74, basically a C-band radar, for all practical purposes. That happened because the manufacturer of that radar was a good friend of one of the political appointees within NOAA. And so the program stopped literally for 9 months while it went through a separate independent evaluation, bringing in Lincoln Labs, bringing in the Air Force Technical Evaluation Team, bringing in MCAR, all of that to take a look at it. The suggestion was totally repudiated, and so finally we got back online again. But it was that kind of thing that started.
And slowed it down.
And slowed it down, and it happened one more time before it was all over. They stopped it one more time before it finally went forward.
So you mean that Wichita Falls wasn't enough?
Wichita Falls wasn't enough, Vance Air Force Base, JDOT wasn't enough, but the thing that actually gave the final approval to go forward with the production phase of the radar occurred in 1985, August the 2nd, when Delta Flight 191 went down at Dallas-Fort Worth Airport with a loss of 138 people, if I remember correctly, on board. It was caught in a downburst in a thunderstorm. The pilot took off regardless of the fact that several other pilots hadn't taken off around it, but he didn't have any information that convinced him that he couldn't take off through that.
Actually, he was approaching the airport.
Yeah, I guess you're right, but in any event, the loss of everybody on board. The next morning, Dick Halgren, who was the director of the National Weather Service at the time, and I was his deputy, we were sitting in his office. We got a call from the Office of Management and Budget, financial analyst that handled the National Weather Service. And this is a direct quote. I remember it well. It's been actually etched in my memory. All right, you've got your damn NextRad. That was the approval process. I found out after talking to the analyst later that what had happened the day before is that after that loss of life occurred with that thunderstorm, there was a big meeting internally in OMB, and they said, what can we do about this? This is not the first one of these that's happened. The analyst said, well, National Weather Service has been trying to put new radars out forever. Well, let's do it. That was the decision process internally in the Office of Management and Budget. It is unfortunate that in order to make progress, in many cases in the federal budget, blood has to be lost, and that was the case here. But that was the approval process for the next draft. We went forward from there and continued the process. And in my opinion, it's been one of the most successful programs I think I have ever been a part of, ever seen. Every time we would put a radar in a new location, we would end up finding out more about mesoscale meteorology than we had known before, because we would see the local phenomena there. The fact that it was animated, the fact that it was high resolution, color, all of those things gave us a visualization of what was going on in the atmosphere that we never had before. And that work was all developed here. It was built by a contractor, but it was developed. The technology was developed here at NSSL.
And of course, that radar's been continually improved and upgraded, and so I want to talk about DualPOL a little bit, Dushan. What's the big deal about DualPOL?
Well, this adds one additional piece of information. You had power effectivity that tells the rain, there is rain or hail, and you have motion. Now, the DualPOL allows determination of what type of scatterers, what type of hydrometers are out there. You could tell wet snow, dry snow, you could tell birds or insects, biological scatterers like those. You can tell reflections from the ground. You can tell hail and discriminate size among the large and giant. And it can improve tremendously the quality of the data, because you can separate meteorological contributions, the ones that are of interest, and you can quantify them better. If you know that there is rain somewhere, then you can use an appropriate relation that to relate this return to the amount on the ground. If you know that it's hail, you can tell roughly the size. If you know that it's snow, I believe that we can even tell better the snow rates on the ground. So that is a new type of information that tells what's in the cloud and where. Whereas before you knew that something was in the cloud, and you knew that there was a lot of that something, or maybe that something was big, but you couldn't tell precisely what exactly that something was.
So we can, one of the things that you just mentioned was you get really improved rainfall estimates.
You get improved rainfall estimates. What meteorologists like also very much is you can tell when the tornado has touched ground and is lofting debris. So that was an unintended consequence of all this work on DualPOL that started with the idea to improve measurements of precipitation. But that's one of those things that they like very, very much.
So Joe, when you're mentioning that 8-to-1 return for an investment in X-ray, didn't that include rainfall and the hydrology component?
It included rainfall for water resources management,
Yeah.
for the stream flooding, all of both the hazards as well as the economic benefits, agriculture, all of these sorts of things, the improved understanding that.
Okay.
And indeed, that's been a very important area of use of the radar.
So to wind this thing up a little bit, this whole effort involved a huge number of people. I mean, it's just amazing when you think about it. 3 agencies, people in government, people in universities, people in the private sector. Who haven't we mentioned? Who should we bring into this success story of what happened?
People
in
or
society?
organizations?
I think people.
Well, to my mind, for example, John Carter, who was initial engineer, junior engineer, worked with Dale, and he was very, very important in instrumenting and making some modifications on the similar radar that made it into a dual polarization radar. And I did mention Alan Zahari, who later became a chief engineer, and had a lot to do of putting new processors. Obviously, he continued doing work on the similar radar, developed the display. And an important aspect that was in 1990, 1991, 92, was the first time ever that a radar could be remotely controlled, weather radar from Norman, 40 kilometers away was similar radar, and the display of data was passed back to the normal location. So you could turn on the radar and look from normal what's happening outside. And the important part of that is Cimarron had a dual polarization capability. So we were very anxious to collect some of this data. And then Alan worked later on the signal processors and improvements of those for the next generation of processors on the next side.
And I don't think we can forget about the technicians that wired all this stuff together, like Glenn Anderson and Mike Schmidt. And there's more that I probably wasn't familiar with because I wasn't here at the time. But these folks had tremendous contribution into making everything happen.
I also mentioned Gene Walker, OU, because he was a consultant to, and he kept advising and pushing Edwin Kessler to support the Doppler program.
And then we had our colleagues at AFGL. Graham Armstrong was a great engineer up there. Al Bishop was a microwave engineer up there. We had our folks at NCAR that contributed a lot. Jim Wilson comes to mind, and what was Gray's first name?
Grant Gray.
Grant
Grant Gray, and I know
And
that
our colleagues.
I've got a whole list here of folks that we probably should recognize at some point.
Our colleagues at the WPL, Dick Stroud and others, we benefit from discussions with them, and they benefited with our discussions. So,
Herb Babinski. Well, earlier on, we were saying that we should focus on NSSL and OU link,
Well,
but we can extend it beyond that. And
I want to bring us back to that. Who wants to talk about Ed Kessler? What was Ed Kessler's contribution to all of this?
I think he was always supportive of the Doppler radar program, and especially when Roger Lermite left, there was a lot of pressure on him to give up the development of Doppler radar. Let Boulder, they had engineers there, and Lermite had actually moved to Boulder, and keep the laboratory, meteorological laboratory, and let the WPL, Wave Propagation Laboratory, do the construction and bring the radars here and do the. But I think Ed Kessler wanted to have the program 10 centimeter and not 3 centimeter, which was a favorite by some people. And he wanted to keep Dale Sherman and John Carter and the engineering group here.
So who conceived of the program? Who wanted
I think
Doppler radar to be part of NSSL?
I want to add something to Dick's, and maybe that's correct. Because really, when Ed was given the directorship, he had to make some decisions. He made a decision, right decision, to latch onto the Doppler and 10 centimeter wavelength, and we divided the wavelengths, the spectrum. NSSL got 10 centimeter, Boulder, Gordon Little got shorter wavelengths. So that's what they divided. That was a gentleman's agreement. It turned out that our choice, that Ed Kessler's choice, was a better one. And it showed at the end. So really he was behind. Plus, if you recall, he wrote about this. Ed was very anxious to make sure that he's doing the right thing. So invited people from MIT Lincoln Lab to come and consult and inspect and give him advice of which is this the right way, is it doable? And they certainly were affirmative, and he was
I
at
read
peace.
about that. He had an early lab review before there were even lab reviews.
Yeah, but he did it on his own
Yeah.
too.
Yeah. Any final words?
Well, we mentioned Ken Wilk, but maybe we could say a little more. Ken was the head of early radar development for Ed at NSSL. Even before we had Doppler, there was
Even
research
before
going on with what was then the operational WSR 57, headed by Ken. And then Ken played a role in the Doppler development. And the first transition that NSSL provided to what became the Next Red Operational Support Facility, the IOTF, Ken Wilk headed that, along with Doug working.
Ken was the first NOAA employee in Norman. He actually preceded the establishment of NSSL. He ran what was then called the Radar Lab out of Kansas City.
with the radar out of North Bay.
And Jim Lee was very important in relating Doppler observations to aviation. So it's another
Right.
old timer, yeah.
I'd like to also point out the fact that the development of the radar and the implementation of NextRad, I think, is one of the best examples of real, true research to operations, because the whole research program started by training the operations people at the beginning. JDOP, for example, the Doppler project that we had here, all of the risk reduction activities that went on at Norman with information from NSSL going directly into the forecast offices to be used in real time. The training activities that we set up here, bringing literally every forecaster in the National Weather Service through the training programs
For a
here.
month.
For a
Month of
month.
training.
We took over the home hotel,
Marriott.
the Marriott
Yeah.
Residence Inn. We took over that for 2 years and ran people through that program. And that made it work. Then, to continue, I have one other story that I want to tell, because it's on Zernich.
Zernich.
Zernich, I'm sorry.
Thank you.
Zernich came to me at an AMS meeting one time in Dallas, Texas.
Nashville.
So was it Nashville? I thought it was, whatever it was.
Because it was
One of those.
95.
I know this story.
He came to me and he said, "We need to have breakfast." I said, "Okay, let's have breakfast." And he said, he had all kind of data he wanted to show me about things that needed to be done. He said, "But we can't help you unless we have an X-ray radar." X-ray radars were about $4 million a piece there, and there was no way I could come up with $4 million. But I went back to our folks in Silver Spring, and I asked Merritt Tector, I said, "What kind of spare parts do we have?" And he said, "Well, we've got quite a few, because the Air Force decided they didn't want the couple of radars that they were going to put in Korea." He said, "So we've got some in pretty good sized chunks." I said, "Send enough of those chunks down to Norman so they can assemble an X-Rad radar." And I said, "I don't want anything in writing on this." I just transferred the things down. And I called up the head of OAR at the time, and I told Ned Ustinso, who was the head of OAR, I said, "Here's what I'm doing, but I don't want any credit for it. I don't want anybody talking about it, because I don't have the authorization to do it." But we managed to get $4 million worth of spare parts down here to assemble a radar. And it's that radar capability, it was that research capability that allowed the development of such things as DualPOL, allowed the upgrade of the processors that have occurred, and all of the improvements that have been done on that radar as a result of the NSSL
Continuing to be.
efforts, and continuing to be done.
Exactly, and I'm eternally grateful, John, for this, because I built a career on it. It was just the
Comment,
greatest.
you called the acting director of the OSF and said, "Take all that equipment across the street and let them set it up."
I don't know, I don't remember
You did.
those details.
That was me.
So
Okay.
that's how NSSL got their own NextRad that formed the basis for all the.
Well, then we
R&D
traded
done.
that with Roch, we traded it for, because it was
More up to date.
more up to date, but we got the radar basically and demonstrated.
Well, I certainly want to thank, I'm sorry.
Oh, we ended up with the first article and they ended up with the spare parts and built the newer version. Yeah,
They didn't tell me they did that.
yeah, well,
So we're going to draw this to a close. I want to thank all of you for taking time, I know from your busy schedules, to participate in this, and I hope this was considered a successful project.